Hello everyone. So today we are going to be discussing or having a lecture on continuity. Yes, limits and continuity. And yes, let me try to write something down here. Okay. So we can say so what I was doing. That is limits and continuity. Okay. So 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 we start with what it means for a function to be continuous. So if a function is continuous and you sketch the graph, suppose you have a function that is continuous and you sketch the graph, then look at this graph now. This graph, yes, so it is a graph of a continuous function. I mean, there is no break, no jump. Yes. So this this graph is it represents or it depicts graph of a function that is continuous. And that function that whose graph is continuous is something like this. Yes. So this is a graph of a continuous function. Alright. So and the question is, what if it is not continuous? So if it is not continuous, let me show you in the next page. Okay, let me try to um, sketch one more graph that depicts a continuous function. If you have something like this is a continuous function because there is no jump. The graph is smooth. Yeah, it is smooth, so no jump, and it is yes, it is continuous. So here I'm going to show you a graph of a function that is not um, that is discontinuous, or that is not continuous at any point. Let's say at the point C now. Okay, so if if this is your graph here, and that assume there is a hole here. Okay, such that okay, this is now the graph. So this graph is discontinuous because there is a jump, there is a hole at this point. Let's say point C. So this graph is not continuous. So this is a function that is discontinuous at a point C because of the hole. Okay, another graph that is not continuous is when we have a jump. Suppose this is a graph and this okay, this graph now, if this point is point A and this is point C, and okay, yes, so this graph is actually, it is discontinuous at point C. You can see that this is not smooth, they are not connected, just like here they are not connected, there is like a hole, and this is what we call is a type of discontinuity known as hole discontinuity. Hole discontinuity. And one thing about this type of discontinuity is that it is removable. Yes, but this one, this is because there is a jump, like a bridge now, so there is a jump, so this is known as a jump. We call it jump discontinuity. Yes, it's a jump discontinuity. Another type of discontinuity that we have is yes, I think we have infinite discontinuity, and that is, how does that look? Yeah, let me try to graph that as well. So if we have something like this, okay, all right, and yeah, if this is this, all right, so this is an infinite discontinuity. Okay, these are the three types of discontinuity. Now let's try to solve questions. So in the questions, we are going to be showing whether a function is continuous at a point or not. So we are going to start with the three tests for continuity. So there are some three things to check, and for us to know whether a function, okay, yes, so we say three tests for continuity. So all right, and here we are. So the first thing, okay, let me just write this. A function f is said, it is said to be, yes, to be continuous, said to be continuous at C, yes, at this point. So C, if, yes, if and only if, one, if f of C is defined, oh sorry, if f of C is defined, that's the first thing that must happen before you can say that a function is continuous. So if f of C is not defined, that is, if f of C is 1 over 0, then it is not continuous. You don't have to try to solve for that. So the first thing that you check is check if f of C is defined. That is, if you find f of C, if you wouldn't get 1 over 0, okay? So if it is going to give you 1 over 0, then it's not defined. That is an infinite discontinuity. You know, we mentioned three types the other time. That's an infinite discontinuity. And if f of C is now defined, then you go for that. You know, there are three tests. Test 2 is you check if the limits of let me get my eraser here. Yes, if the limit of f of x, the limit of f of x, yes, exists. No, as x tends to C, that same point, the limit, you want to check if the limit of f of x exists. Okay, and how do I know, how do I check if the limit of f of x exists? It's this is how to check. You just have to, the limit, if the limit of f of x exists, then it means that the limit of f of x as x approaches C from the left, the limit of f of x as x approaches C from the left must be equal to the limit of f of x as x approaches C from the right. So if this is equal to this, then limit of f of x exists. So that's what it means. And let's check the next page for the next, or for the third test now. So, and the third test is that the limit of f of x as so the third test is now that the limit of f of x as, you know, one of the tests or test 2 is that the limit of f of x must exist. Okay, so that is the third test is now that the limit of f of x as x approaches c must be equal to f of c. That is test 1, 1 and 2 must be equal. So, and that is that about that. So these are the three tests that must be carried out. So if a function is now said to be continuous if it passes all these three tests. So these are the required courses that a function must pass at a point before we can say that, oh, you are continuous. Okay, and let's check some worked examples so that it will not just be that we are. Let's check some examples. Okay. All right. So we want to verify. So verify the continuity. Yeah. Of the following. You have the following functions. Okay. And the first function that we have is, well, the first function is, yes, f of x is equal to x squared minus 1, I guess. Yes, I got that right. Over 3x squared plus 2x, and I think minus 1, yes. So we want to verify whether this function is continuous or not at points that's to be at a particular point at x equals to 1. So we want to show whether this is continuous at x equals to 1 or not. Meet me in the next page, please. So we need a fresh page for this. We need to check the first test. So we'll begin with the first test, which is we want to know if f of, at which point f of 1, and the point is not c now, it's no longer c, is 1. Now we have a defined point. So we want to check what f of 1 will be, and if we do direct substitution, since it is x squared, that will be 1 squared minus 1 everything over 3x squared, and 3 into bracket 1 squared, now plus 2x, 2 into bracket 1, and minus 1. Okay, and this should give you, on top we have 0 over, this should be 3 plus 2, 5 minus 1, 0 over 4, and 0 over 4 is 0. So you can see the answer is not 1 over 0. So it means f of, so that means f of 1 is defined. So it is not undefined. So it passed the, let me say CA1, the first test. Okay. And the second test is to show if we want to know if f of x, the limit of f of x, that is the limit of f of x as x tends to 1, as you want to know if this exists. So this is the second test. Now, since the question is this, let me write the question again. Is the limit of x squared minus 1 everything all over 3x squared plus 2x minus 1 as I think x tends to 1. So this is a question. So the first thing we need to do is to what's the first thing here? Okay. Yes, okay, I think the first thing that we need to do is to find a way to, yes, to check if this exists. So, and yes, we can just try to solve this. And I think we can solve this by factorizing. Yeah, we can solve this limit by factorizing. So using factorization method, okay. So, and what does that mean? So that means we have the limit as x tends to 1. Here we have x squared on top. Okay, x squared minus 1 squared. Okay, and this gives 3x squared plus 2x minus 1. Okay, so you try to solve what you have here and what you have on top, and by so doing you should get. Now to factorize this, we have, yes, we are going to factorize what is on top and what is at the bottom. So we have the limits as x tends to 1. Here, this using difference of 2 squares, so this should be x minus 1 and this should be x plus 1. So what we have at the bottom, to factorize this, we multiply this by 3 times minus 1, this should give us minus 3. Then you look for the factors of 3, whose sum will give 2x. Now you know how we do quadratic or factorization of quadratic expression. Okay, so and if it is minus 3, 1 times 3 plus 3 minus 1 will give us plus 2, and that should be plus 3x minus x minus 1, and this will be the limits as x tends to 1 of x minus 1, and here we have x plus 1. And if you do the factorization under here you bring out 3x, so you now have 3x into bracket, I think x plus 1, yes, I got it, and here you bring out minus 1 into bracket x plus 1. Okay, so let's meet in the next page, please. And now we have let me take my pen. So now we have this to be equal to the limits, okay, as x tends to 1 of okay, I think on top we have x plus 1 and x minus 1, so everything over. So now we have 3x plus, no, 3x minus 1, then x plus 1, yes, so and obviously this will cancel out, then we are left with the limits as x tends to 1 of x minus 1 over 3x minus 1. So we can now substitute, and that we have a simplified formula. And when we substitute x for 1, so we still have 1 over 1, everything over 3 into bracket 1 minus 1, and this gives 0 over 2, which is 0. Hence the limit exists and the answer is 0. Okay, so now to check for the third condition, third condition says that the limits as x tends to that point, which is 1 now, of f of x must be equal to f of 1. And if you slide back, you will discover that this is equal to 0, as we just did, and this is equal to 0. Yes, then it means it satisfies the 3 conditions. 1, the limit of f of 1 is defined and the answer is 0, and 2, the limit of f of x as x tends to 1 exists and the answer is 0. Then 3, both of them are now equal. So we can now say that hence it is what? It is continuous. Hence it is continuous. Yes, another way to show that, to show condition 2. Condition 2, we want to check whether the limit of f of x as x tends to 1 exists. Another way to show it is to just show that the limit as x tends to 1 from the left is equal to the limit as x tends to 1 from the right. In the next example, we are going to show that. So you should follow with me. Example 2 now. Let us show, given that f of x is equals to absolute value of x at x equals to 0. So we want to show if this function is continuous at x equals to 0. Okay, and we have 3 tests. The first test, so we need to know if f of 0 at that point, if the value of the function at the point we are considering, which is 0 now, is divine. X will be equal to 0, and this is 0. Hence, f of what? F, the function is defined, and the answer is 0. Alright, so the function is defined and the answer is 0. And moving on, so B, we want to check if the limit of f of x as x tends to 0 exists. So we need to check the limit as x tends to 0 from left, the limit of f of x. We said if it is equal to the limit of f of x as x tends to 0 from right, then if these are equal, then we can say that the limit exists. Okay, so, and we are going to do this by checking the graph of f of x. So f of x, absolute value of f of x, this is how the graph looks like. Okay, so this is the graph. So this is the graph, and x tends to negative infinity, from negative infinity to infinity. So, and this is on this graph, so this is the value of the function at any point, at any value of x. So this is the value of the function. In this point now indicate the value of the function f of x at any value of x. Okay, so but looking at this graph, you can see that this is point 0, the point we are considering. So if we move further to the left, so the value of x is getting more negative, and from here to the right hand side is getting more positive. Now let us check if this is true. So we want to check if the limit of f of x as x tends to 0 from the left, if x is tending to 0 from the left, now from negative infinity, so it means I have to move like this. I'm moving. Do you get it now? X is tending to 0. X is approaching 0 from the left. And if x is approaching 0 from the right, so it means I'll have to start from this and begin to move like this. X is approaching 0 from the right. So we want to check if this is equal to this. Alright. And looking at this, you can see that the limit of the function as x approaches 0 from the left, x is approaching 0. So if x is approaching 0, the function is also what? Approaching 0 from the left. Now, as x is approaching 0 from the right, you can see the function. This is a function. The function is also approaching 0 from the what? From the right. So it is safe to say that the limit of f of x as f approaches 0 from the left, x is approaching 0 from the left, then the limit is what? Is approaching 0. Okay, and also the limit of f of x as x approaches 0 from the right is also 0, because x is approaching 0 from the right, and you can see that the function is also moving towards 0. And so I can say therefore the limit of f of x as x approaches 0, it's what? It exists, and the answer is what? Is 0. Okay, so let's move on to the third test. Then the third test is to check if the limit as x approaches 0, the limit of f of x as x approaches 0 is equals to f of 0 now. And you can see that, okay, it's actually true. 0 is equal to 0. So therefore, f of x equals to absolute value of x is continuous. Is actually continuous at x equals to 0. All right. So let's move on to another question. This question is piecewise function. Yes, piecewise function. So we want to show, it's a very interesting question. So we want to show if square root of x plus 2. Okay, they give us this question. The function is like this. Okay, and here we have x squared minus 2, and this is 2 less than or equals to x less than 3, and finally we have 2x plus 5, and here we have x greater than or equals to 3, I guess. Yes, so we want to show if this function is continuous. Now show that this, okay, is continuous. To show if this is continuous at 2, and okay, these are two questions embedded here, at 2 and at 3. Okay, so to begin with, at point 2 now, and the first condition, the first test, so it's like CA test. So the first test that we have to do now is, check if f of so at point 2, so we want to check if f of 2 is defined. Okay, now to find f of 2, they gave us 3 functions here. This is, okay, 3 expression. Okay, the first expression, second expression, third expression. So which expression are we going to use to find f of 2? This is the question. And look at the first expression, the values of x. This is when x is less than 2. Here, this is when 2 is less than or equals to x. So here we can see that x is equals to 2. I mean that one of the values of x is 2 here. 2 less than or equals to x. So this is the right expression because of this. Now for the third one is when x is greater than or equals to 2. So there was never a time when x equals to 2. Sorry, x is greater than or equals to 3. There was never a time when x equals to 3 here. For this, there was never a time when x equals to 2, because the values is when x is equals to 2, and the whole number values will now be 1, 0, minus 1, minus 2, onto infinity. Now for this, when x is greater than or equals to 3, this will be 3, 4, 5, 6, onto infinity. This one is onto negative infinity. But here, 2 less than or equals to x less than 3. So the first value here includes 2. So this is when x equals to 2, and this is the right expression. And because of that, this should be x squared minus 2. But since f of 2, we substitute 2 for x, and that will now be 2 squared minus 2. That should be 2. Is that taken? Then this is it means that f of x is defined, and the answer is 2. Okay. Now for the second test, for the second CA, okay, so we want to check the limits of if limit of f of x exists. And to do that, we need to know the limit of f of x as x approaches 2 from the left. So when x is approaching 2 from the left, we have to use one of these expressions. But which one is suitable? Okay, can we use this? This is when this is the expression, and it is when x is less than 2. If x is less than 2, so it means those values, they are approaching 2 from the left. Is that taken? Yeah, x is less than 2. So this is when x is less than 2. The values are like from negative infinity, and we have minus 1, we have 0, we have 1, and just before it gets to 2. So this is a suitable expression. This one is 2 less than or equal to 2, x less than 3. So this one is it begins from 2 and it's tending towards 3. Is that taken? But for this is x greater than or equal to 3. This one is from 3 and it's moving away from 3, like 3, 4, 5. So it is not the best expression. It is not approaching 2 from the left. So this is when x is approaching 2 from the left. X is less than 2, so it's moving towards 2, but from the left. So we use this expression, square root of x plus 2, and that will now be square root of, what's our x now? 2 plus 2, and this should give 2. The square root of 4 is 2. Then we check for the limit of that same function, but when x is approaching 2, but now from the right. So if x is approaching 2 from the right, so of course we cannot use this, because here x is not approaching 2 from the right. Now can we use this? Is x approaching 2 from the right? Yes, we can use this. Here x is approaching 2 from the right. You can see that the values of x here is 2 and moving towards 3. So this is how to sketch it. 2, close interval here, comma 3. So this is what we have for this. Now for this one is 3, comma infinity. Yes, positive infinity. So here, the values are 3, 4, 5, 6, 7, 8. Is moving towards infinity. So but here the values are 2, comma, then like 2 point something, or just before you get to 3. 3 is not included. So the values of x here, they are approaching 2 from the right. Yes, you can see this is greater than this, so it's approaching 2 from the right. But as for here, the values here, they are greater than 2, but they are more they are farther from 2 compared to this. Is that taken? So here this is actually a suitable expression for when x is approaching 2 but from the right. 3 is moving to, like, the values are moving towards 2 but from the right. This one is like the value are moving away from 2 now. 3, 4, 5, they are getting bigger. Okay, so now here we have the expression to use here would be x squared, but what was x squared now? 2 squared minus 2, and this gives us 2. So therefore we can say the limit exists. Here the limit exists. since what was it gonna the left the limit of f of x as x is approaching 2 from the left is equals to this, then the limits, we can say the limits of f of x now as x approaches 2, it exists and the answer is 2. So the limits exist and the answer is 2. And the third test now to check is if the limit of f of x, as x approaches that approaches to, like the limit of f of x as it approaches to, if it is equal to f of 2, and they are equal because f of 2 is 2, the limit of f of x as x approaches 2 is also 2. So therefore the limit was the function is continuous because this is equal to 2 and this is also equal to 2. So we can say that f is what is continuous. F is actually continuous at don't do that, at this point, point 2. And let's move to the next question. And maybe let's write the question again. This is f of x. It is a piecewise function, and we have here, I think this is x plus 2, and the value is x. Let me check my notes. Yes, x less than 2, and here we have x squared minus 2, and this is 2 less than or equal to x less than 3, and this is 2x plus 5, and this is x greater than or equal to 3. Okay, so we want to show if it is continuous at point 3. Yes, at 3 now, not 2. So for 3, as usual at the first test, let's check if f of 3 is defined. Now for f of 3 here, f of 3 will be, it has to correspond to when x equals to 3. Here, the values of x, they are 1, like if we consider the whole number values, x is less than 2. So x has a value, or it has values that are less than 2. So we can consider 1, 0, minus 1. So there was no point when x equals to 3. Here, the values begins from 2. Is 2 less than or equals to x less than 3. So it begins from 2, so, and just before it gets to 3. Here it does not, we don't have x less than or equal to 3. So x is not equal to 3 here. But here we have x greater than or equal to 3. So the values of x here, the whole number values of x here will be 3, 4, 5, on to infinity. So here, so that this is the equation that corresponds to when x equals to 3, and this is what we are using. So that one will be 2 into bracket. Now x equals to 3 plus 5, and this should be equals to 2 times 3 will give us 6. So get 11. Okay, and so f of x is defined. Now let's move on. We want to check if the limit exists, and that we do by finding the limit of f of x. Yes, the limit of f of x as x approaches 3 from the left. So we want to check if it is equal to the limit of f of x as x approaches 3 from the right. Now we need to look for, okay, what are the expressions to use when x is approaching 3 from the left. Let's come here. If x is approaching 3 from the left, now here, the values of x are, they are what? They are 1, like 1, 0, minus 1. So those are the values of x. Okay, so here the values of x, okay, they start from 2 and is going towards 3. You begin from 2, is going towards 3, and this is just perfect for when x is approaching 3 from the left. I mean from a smaller value to 3 now. Okay, unlike this one that is just moving away from 2, so it's getting smaller, so it's not getting bigger, so it's not moving towards 3. Okay, but here the value begins from 2 and it's going towards 3, so this is what we are going to use. And here we have x squared, that will be x squared. And what is that x now? So that will be 3 squared minus 2. So we want to check if it will be equals to, now when x is approaching 3, now from the right, and this is just the, okay, where is x approaching 3 from the right? This is just what we are going to use. You know, if it is approaching 3 but from the right now, okay, and you know the values of this, we can say, okay, from infinity like 5, 4, 3, and that's the benchmark. It cannot go below that because it's x greater than or equal to 3, and this is just the expression to use. So, and what was that expression? 2 into bracket 3, so that will be 2 into bracket 3 plus 5, and this gives what? 9 minus 2, that's 7, but 7 is not equal to 11. So we don't need to test for that. This limit is, I mean the function is not continuous at 3. So it is discontinuous at 3. Okay. And what kind of discontinuity is this? You know, we have infinite discontinuity, there is O discontinuity, and there is jump discontinuity. So what you should know is that if f of x is not defined, that is if f of x is 1 over 0, okay, then this is an infinite discontinuity. Okay, so but if this is not equals to this, okay, this is a type of okay, the type of discontinuity is a jump discontinuity. I call it jump discontinuity. Is not infinite. Yes, infinite is when f of x is undefined, but it is defined. But what just happened is that this is not equals to this. So if this is not equals to this, it means the limits of f of x as x approaches to does not exist. So the limit does not exist, and we have the kind of the type of discontinuity is a jump discontinuity. It is jump or non-removable. Yes. And the last question for this class is if we have, oh sorry, where's my eraser? So if we have this question, so we want to show if f of x, this function is also a piecewise function, if it is continuous, and that's 2x plus 5 at x equals to minus 1, is x less than 1, x squared plus 2, and x is greater than minus 1, and here 5 at x equals to minus 1. So we want to show if this is continuous at x equals to 1, and as usual, the first test. So at x equals to minus 1, yes, we want to show if it is continuous at x equals to minus 1. So we find f of minus 1, and if you look at this, f of minus 1, so that will be when x equals to minus 1 and x equals to minus 1. When x equals to minus 1, the function is 5. So the answer is just 5. So since the answer is 5, that means this is defined. Okay, then we'll move on to check if the limit exists. And if the limit exists, then the limit of f of x as x approaches minus 1 from the left, okay, must be equal to the limit as x approaches minus 1 from the right. Okay, now for the limit of f of x as x approaches minus 1 from the left, this is what we are going to use. Now this is x less than minus 1. This is when x is approaching minus 1 from the left, and that will now be 2 into bracket x, then we have minus 1 plus what? Plus x. So we want to check if it is equals to, when x is approaching minus 1 from the right, then this is what we have, and this is what we are using. And now we have minus 1 all squared plus 2. Okay, and this gives minus 2 plus 5, that should be 3, I guess. But 3 is not equals to, this is 1. This is equal. And this is minus 2 plus 5. Yes, that should be 3. And this should be 1 plus 2. And this is 3. Oh, sorry. They are equal. So if they are equal, then it means we can now proceed to check for the third test. For the third test, all we need to check is if the limit of f of x as x approaches minus 1 is equals to f of minus 1. Now this is equal to 3. You can see that this exists, limit exists, and the answer is 3. So, but it's not equal to f of minus 1, which is 5. So it means this limit does not exist. And this is another type of jump entirely. What kind of jump is this? The third. Can you guess? Whole. The first was infinity. Infinity is when this is not divine, but this is divine. For the jump discontinuity is when this does not exist, but this exists. So this third type of discontinuity is jump discontinuity, and this is a jump discontinuity. So it is not continuous at x equals to minus 1, as it does not satisfy all the 3 requirements.